Bismillahirrahmanirrahim. I am Dr. Muhammad Adnan, working as Assistant Professor in the Department of Physics, Cohort University of Science and Technology. I welcome you to the course PHY 103 Waves and Oscillations. Today, it is the 10th lecture of this course, and the topic is waves and its properties. First, I will give the learning objectives. At the end of this presentation, the student will know the various types of waves. They will be able to distinguish between the transverse waves and longitudinal waves. And also, the student will be introduced to the wave variables, which are essential for the wave mechanics. This will be more of a descriptive type of lecture in which we will be discussing the various terminologies associated with the waves. In this course, we are following the book Fundamentals of Physics by Holliday, Resnick and Walker, 10th edition. Some of the illustrations are taken from this book. Well, so we will start with the definition of a wave that can be described as a disturbance that travels through a medium or a space, transporting energy from one location, that is from its source, to another location without transporting matter. So the first thing is that why we are interested in waves. So waves are important because it transports the energy from one location to the other location. Now, one can have different types of waves depending upon the transport mechanism. So the first one is the mechanical waves. Now, these waves are most familiar because we encounter them most commonly. The example includes the water waves, the sound waves, the seismic waves. In all these waves, two central features are there. That is, they are governed by the Newton's laws, and also they can exist within the material medium. So one can say that these mechanical waves are some physical medium is being disturbed, and they can only exist within that medium. Now these waves propagation, the wave propagation is the propagation of the disturbance through the medium. As I told you, the medium elements will oscillate such that the wave will propagate without transporting the medium. The second one is known as electromagnetic waves. Now these are less familiar, but we use them constantly. For example, the visible light, the ultraviolet light, the radio waves, the television waves. These are examples of electromagnetic waves. Now, these waves do not require any material medium for its existence. So no medium required for the propagation of electromagnetic waves, and these are the examples. These waves are constant velocity waves. You have studied this in you have studied this in various courses. The third one is the matter waves that one can uh, understand as the waves which are unfamiliar to most of us, but they are associated with the subatomic particles like electron, proton, and other fundamental particles. And this matter waves are usually discussed in the quantum mechanics, the subject of quantum mechanics, where each particle have a wave associated with it. Now, by looking at these waves and the mechanism, so one can say that the amount of energy and also the mechanism responsible for the transport of the energy, that is the different mechanism which are responsible for the transport, differ in all these waves. So that's why we have different kinds of waves. But in this course, we will be only concerned with the mechanical waves. Now, these mechanical waves are further classified into the transverse waves and also the longitudinal waves. So we will be describing one by one. The first one is the transverse waves. The transverse waves are a wave or a pulse that causes the element of the disturbed medium to move perpendicular to the direction of propagation. For example, in this picture, there is a rope that is connected to this end, and on the other side, if this man just move his hand in which he holds this rope up and down so that he can create these transverse pulses. Now, if he continuously moving his hand up and down, so he will be just transporting instead of a pulse, continuous waves, traveling waves. Now, this spot is just a random spot of this rope. Now, during the wave motion, this point will oscillate up and down, and the wave will propagate towards the x direction as indicated by this arrow. Now, according to this definition, if one want to understand this, that the particle will oscillate up and down, that is perpendicular to the wave propagation. Now the particle motion is shown by that black dot. That will be, this is just a snapshot at this point. At this time, this part was just horizontal position, but it will be just oscillating during the dynamic picture. And also the direction of the propagation is indicated by the pink arrow. So the motion of the particle is perpendicular to the propagation direction. So that's why these waves are known as transverse waves. Now the second one is the longitudinal waves. So again, a wave, a traveling wave or a pulse that causes the element of the disturbed medium to move parallel to the direction of propagation. This time the elements of the disturbed medium will now propagate parallel to the direction of propagation, and that's why these are longitudinal waves. Now this is taken from your book. Now the description is, if someone just suddenly move the piston rightward and then leftward, so it can send a pulse of sound waves along this path, along this pipe. Now the rightward motion of the piston causes the change in the air pressure as indicated by these different regions of dense and diluted portions. The increased air pressure then pushes rightward on the elements of the air somewhat further along the pipe, and moving the piston leftward, as I told you, by doing rightward and then leftward, doing the same thing. That is, as a result, the first element nearest to the piston and then further element will move leftward. Thus, the motion of the air and the change in the air pressure travels rightward along the pipe as a pulse, as indicated by these lines. So we know that the sound waves in air travels through compression and rarefaction. So these molecules, the air molecules, just oscillate parallel to the direction of propagation, and hence they are longitudinal waves. Now one can say that both the transverse as well as the longitudinal waves are traveling waves because they both travel from one point to the other without transporting the material. So after these definition, now we will be in a position to describe the wave variables, the terminologies associated with the wave mechanics. Now, before coming to these technical parameters, first we will be starting with the mathematical descriptions, how one can describe mathematically a wave or a pulse. So this is just a snapshot taken of a transverse waves on a rope. So this shape is taken at t is equal to 0. Let's say at that time we just start t is equal to 0. So it was in this position. This point P is just a random point on the rope, and the wave is traveling towards the x-axis. This A is the amplitude or the maximum displacement of the wave along the vertical coordinate. So this is at t is equal to 0. Now this mathematical function will describe this wave. This is just a random wave for the time being. That will be y depends upon x and t, because this is x and also at which time you are looking at that x. So we are looking at t is equal to 0. So this is just a function that will represent any function. Now, as I told you, that this y will be the transverse position of the element of the string located at each value of x at t is equal to 0. So this will be describing the transverse position of the wave such that this A will be the maximum displacement from the reference line. Since the speed of this pulse is v, so if it is traveling with the velocity v, so after time t, this is taken at t is equal to 0, so after time t, the pulse has traveled a distance vt. So that distance will be, generally we know that x is equal to vt, so it must move a distance vt. So that now that random point P, which was initially at t is equal to 0, in this state of motion, now it is in this state of motion such that at t is equal to 0, it was at 0 amplitude vertically, and now it is having some amplitude that is taken at t. So how one can change the description now? That will be now that x, which is just the transverse position of this pulse at any x and t, that will be just x minus vt, since that is moving with the velocity vt. Now for a pulse moving to the right, the description will be like this. There should be x of t, that is y is a function of x and t, and that depends upon the function. Now we will be describing this in a minute for how this function will be for such kind of harmonic functions. For a pulse traveling to the left, this will be just x plus vt. So generally we can say that the description can be y is equal to f of x plus minus vt, depending upon the propagation direction. But since in this course we'll be mainly concerned with harmonic functions, so this f, which is just the general description, that will be converted to a sine function or a cos function. But in this whole chapter we will be stick to the sine function for describing a wave, such that this ym is the amplitude in this figure. Generally this is a, but now it is ym. Now this function is a sine function. Now this is sine, and then this is known as the phase of this function. Now we have bring this k and omega. Generally, in the general description, there was no k and there was no omega, because once we are dealing with the sinusoidal or periodic functions, so this periodic function repeats its value after some particular interval. So that's why it is convenient to describe this in terms of this k and omega. We will be describing these technical terms on the coming slide. So this is just because the function that we are describing, or the dynamics that we are modeling in this chapter, that will be mostly periodic sinusoidal. So that's why instead of this f, we can have sine function. On this slide, I will be just describing the various components of this function, which is just the representation of a sinusoidal wave. As I told you, this is the general any arbitrary displacement of the wave, which depends upon x and t, such that this ym is the maximum displacement, which is known as the amplitude of the wave. Now this as a whole, this is the oscillating term, the function itself, and this is known as the phase of that function, such that this k is the angular wave number, this x is the position, this omega is the angular frequency, and this t is in time. So this, in writing in this form, can have the sine value in terms of radian, and that is handy to work with the harmonic functions. Now we will be describing these technical terms one by one. So this is the wave function, which I just described, the various terms, the sine function, the phase, the amplitude, and the general vertical transverse displacement. Now we'll be using this figure of any sine wave, where this y is the maximum amplitude of the wave. This point is at maximum amplitude, this one, this one on the negative side, but this ym is the amplitude, the maximum displacement. These are the point for the ym. Now this is lambda. We'll be describing it one by one. This is traveling towards the x-axis. So we'll start with the amplitude and phase. As I told you, ym is the amplitude, so one can define the magnitude of the maximum displacement of the element from their equilibrium positions as the wave passes through them. So that is that maximum amplitude known as the amplitude, labeled as ym. Now the phase is kx minus omega t. The phase of the wave is the argument of the sine function. This is the phase. Now we are discussing different motion in which this omega, the angular frequency, is constant. So this phase will evolve in time constantly. So as the wave sweep through the string element at a particular position, say x, the phase changes linearly with time, as I told you. This means that the sign also changes, oscillating between 1 and -1, as we know that the values of the extreme values of sine function is 1 and -1. So at extreme positive value, that is when the sine and then this is the phase, and if one evaluate this sine function and it gives us value 1, that will be the peak value of the y at that position x, right? And similarly the -1 will be the minus m, but the ym is a positive number. Now generally we know that the phase is just the represent the portion or the element of the wave state of motion. So for example, if we mark uh, different points on this wave, so every point will be in different state of motion, such that, let's say, uh, if we just connect a rubber elastic arrow to this rope, such that at this particular time, let's say that arrow points upward, and there is another arrow on this position, so that in this state of motion, that will be, the arrow will point downward. So one can say that they are at the same amplitude position, but they are in different state of motion because they are out of phase. So there will be a phase difference of 180. For example, that arrow points upward, and then this arrow will point downward. So there will be a phase difference of 180. So if you see, one can see the different position will be at different phase. So that you can work out. Now after that phase and the amplitude, now we'll be in a position to describe the wavelength and the angular wave number. That is, wavelength is lambda and this angular wave number is k. So this lambda can be defined as lambda, the Greek word for the wavelength, is the distance which is parallel to the direction of the waves, in which direction the wave travels, between repetition of the shape of the wave. This is just a point. One can define this lambda as a point on the successive pulses having same state of motion. For example, this point and this point is just the adjacent point having almost the same amplitude, but their state of motion will be different. So this position is, for example, and this position is in same state of motion, and they are lying on the adjacent pulses. So that is lambda. One can mark from this point to this point because this point 0 and this point is also at the same amplitude but also same state of motion. So that is 1 lambda. So that is a technical parameter. So if one describe this wave at t is equal to 0, so as on a previous slide I've told you that that will be y x t is equal to 0, and generally that was f of x. Now we have ym sine of kx. Since t is equal to 0, so this part will be 0, so it will be left with ym sine of kx. Since the displacement y is the same at the both at both ends of this wavelength, that is, the displacement at x is equal to x1 is this much, and then this point will be x1 plus lambda. This will be, now the two amplitudes are the same as I told you, and also the same state of motion, phi is also the same. So so that the amplitudes are the same, so one can calculate the y equal to x plus lambda as well, and the two amplitudes are equal, so then one can equate the two such that that one is y1 and the other one is y2. Since they are equal, so y1 is equal to y2. So we have just moved x, first it was x1 and then we have added lambda to it such that the amplitude remain the same, so one can equate this. Now if one multiply this k here such that this will be k times x1 plus k times lambda. But since we know that at the beginning I told you these harmonic functions repeats its value after some particular interval, so we know that the sine function begins to repeat its value when its angle is increased by 2 pi radian. So it means if this function repeats its value after you add lambda to it and it comes out the same y, it means this is equal to 2 pi. That's why the value kx plus 2 pi will be the same. That is sine of kx 1 and then sine of kx 1 plus 2 pi, that will give you the same value. So this means that this factor k times lambda is equal to 2 pi. So by rearranging it, one can obtain this k, the angular wave number, is 2 pi by lambda. So this is like a number of waves in 2 radian. That is just the 2 pi comes from the one complete cycle. That is, one can for an oscillatory motion having this omega as constant. So 1 lambda, that we will explain on the coming slide, that if a particle covers 1 lambda, so that is equal to, like, it is moving on a circle and it completes 2 pi radian, because lambda is a distance which the harmonic function travels in one period. So if one just describe this k, so this is called a wave number defined as the reciprocal of the wavelength. That previous case was the angular form. It just represents the number of cycles per unit length. For example, in this picture, let's say lambda is given as 0.5 centimeter. That is, these are the adjacent point on the adjacent pulses having the same state of motion. So one can say that this is lambda. So if 1 over lambda is calculated, so that will be k, the wave number. So we will, if lambda is given in centimeters, so this 1 over lambda, that is 1 over 0.5 centimeter, comes out to be 2 centimeter inverse. That is, we will be having 2 cycles per centimeter. So for example, this is total distance is 2 centimeters. So per centimeter, that is, this will be 1 centimeter. So in 1 centimeter, how many cycle we are having? That is the value of k. So let's see, this is 1 cycle and then we have another cycle. So in 1 centimeter, because lambda is given in 1 centimeter, so in 1 centimeter we are having 2 lambdas, that is 2 complete cycles. So this is just showing the number of waves per unit length or per unit centimeter or meter. After that, we will be describing the period, the angular frequency, and the linear frequency. So for that, again, the pulse is shown, but now this is not a snapshot. This is against t. That is, if one just localize a part of a rope, that is one particular position, such that we only see that one part of the rope. So when the wave is moving across that rope, so one will see that point or that element of the rope which is only visible to us, that is just oscillating up to here and here. It will be just moving an oscillatory motion. So if one plot that behavior of oscillatory motion against time, so we'll be getting a pulse like this. Now, to explain that, we want to describe a wave at x is equal to 0 at any time t. So this x is equal to 0, and now since sine of minus theta is minus sine theta, So that will be minus ym sine of omega t at x is equal to 0. So putting x is equal to 0, one can have this kind of expression. Now we define the period of oscillation t of a wave to be the time any string elements takes to move through one full oscillation. A typical time period is marked like this. This is one period. So one lambda distance is covered in one time period. So that is, if we move to that same example, that we have a one spot on the wave and that is just oscillating. So one complete oscillation will take t time. Now, as I told you, this will be in the same state of motion after t, so that's why the two amplitudes are same as we have done with the x part previously. So one can write that this y amplitude is the same at t1, and then we have t1 plus the time period, so that one can equate the two, and by solving this omega t1 plus omega t, and like previously, as I told you, that this harmonic function repeats its value after some interval, that is 2 pi. So this implies that this omega t is equal to 2 pi. That's why the two amplitudes are the same. So working out with this, one can have this omega, the angular frequency, as 2 pi over t. Now to understand this omega, which is the angular frequency, as 2 pi over the time period, where omega is the angular frequency, the SI unit is now radian, because this is 2 pi radian, and then per second, this is the SI unit. Similarly, the linear frequency is related with 1 over t, and the angular frequency, the three are connected by this expression. One can convert this. Since I told you the harmonic functions are function which repeats its value after a particular interval, so at the beginning I told you that it is handy to bring these k's and omega, so that this is in radian. So these wave motion with the omega, or we can say the phase, are linearly connected with time, constant phase, so that this is like one complete cycle. This is one period. So in one period, it is like if a particle is moving over this wave, so this much is the distance it covers. So it is the same as a particle performing a uniform circular motion with angular velocity v, as we know that for uniform circular motion, the angular velocity and the angular frequency are the same thing. So that it will cover a total angular displacement of 2 pi radian. So that 2 pi radian it covers in one period. So that's why this is like displacement over time, so that it covers 2 pi radian in one complete period. And it is marked. The two are just having similarities. So describing in this way, it is easy to work with these oscillatory functions. Now you need to do this assignment from your course book, and that is from the module 16.1. These are 6 questions. You need to solve these. These questions are based on the transfer waves, such that you will be able to understand how to calculate the phase, how to calculate the amplitude, the angular frequency, and the linear frequency. With this, I thank you very much for your time.